Yes, hello everybody. I'm happy to be introduced by my colleague from Duke, Eamon Marvian. Thanks a lot for the invitation. It's a pleasure to be in Toronto, as always. Yeah, so I'm at Duke University. I am a scientific advisor for IonQ. Duke University tries to look like it's from ancient times, but this was built in 1930. So, okay, why are quantum computers noisy? Usually quantum computers are noisy for very boring things, like your HVAC isn't working, your electronics are noisy. Maybe there's a bad Zoom connection and you try to explain what to fix, it doesn't happen. And then even if we could get rid of all of these things, there's still these annoying vacuum fluctuations, and as we saw recently from like the Google experiments, cosmic rays. What are you gonna do? You gotta do something. So when I think about this problem, I kind of split it into two parts. Which is I'm a physicist and the world is only Hamiltonians. That's it. I might accept a Lagrangian, but usually no. Or I try to think of it from a computer science perspective, and I just think the world is gates. And you're trying to do your gates, and the environment here represented by this is like the mascot of the Duke Library, a devil reading a book. Is trying to do something else to your computer, okay? So today's talk is going to be from the Hamiltonian perspective, though lately I've been thinking a lot about the computer science perspective. All right, so there's a really nice description of quantum error correction by Preskill, which is called fighting entanglement with entanglement. And so I think of quantum control as basically the same thing. We're fighting Hamiltonians with Hamiltonians. I really like this picture from Diego Rivera, man controller of the universe, painted a few years after that chapel was built at Duke. Yeah, you know, chapel was paid for by these rich guys over here in the picture. So the key thing is, first, when you're doing a quantum experiment, you have limited measurement. You're not able to go in and understand all of the noise in the environment, all the controls. You have to do something smooth. Second thing is you have limited control. Like this poor fellow in the photo only has this joystick, right? And he can turn the machine left and right. I think of the environment as kind of these external forces out of our control, always coming in to destroy the machine. And then I think about this kind of utopian people on the right. It's basically our unrealistic model. So we have some belief about how the system should work, but the system actually does whatever it's going to do. Okay, so to me, when I think about quantum control, I just have this really simple picture, which is that I want to make a gate, which is a unitary evolution, and it comes from some Hamiltonian, which maybe varies in time, maybe doesn't commute with itself, which I hide under this time ordering operator. And kind of the beautiful thing is there are many Hamiltonians which lead to the same unitary. Many control systems. So as a simple example, I could just directly apply a rotation about the z-axis, or instead I could apply a rotation about a y-axis and then flip it to the z-axis. Simple things like this. So when we go into the lab, we have a bunch of issues, which is, all of our control side is limited. And then we have the issue which we don't control the environment. Environment belongs to these external forces. Nevertheless, if we take this view that everything is Hamiltonians, life is not too bad. So there's the Hamiltonian that we'd really like to do, which is the ideal Hamiltonian. But we have limited control, so we can think of that as effectively an error in our Hamiltonian. We have errors from a classical environment, errors from a quantum environment. And I just like to separate it into like the good Hamiltonian, H0, and the bad Hamiltonian, which is everything else. And so our goal is basically, can we find operators such that the thing we wanted to do, which is just integrating, the good Hamiltonian for some time, we do with the full Hamiltonian with all the bad parts. And it's possible because all these paths connect back together. Now, the problem is we don't have any, in this kind of generic picture, we don't have any information about this. And so in some sense, like your first reaction should be that it's indeed impossible. So the environment is this massive dragon. You have like, I think this guy just has a broken sword. It's like a minimal control situation, right? So then the solution to this is well captured by the side of this chapel in Basel. So this is in Basel, Switzerland. This is St. George killing the dragon. Key thing you notice is the dragon is like the size of a small dog. St. George is so unscared that these angels are lifting off the helmet. And so from a theorist perspective, you'd say, all right, I just got to make sure that all this environmental noise is bounded strength, slowly varying, and then I'm good to go. And I think there's a flip side from the experimental perspective, which is if you build an experiment that doesn't work, you build a new experiment, right? I think sometimes when I talk to my colleagues doing characterization, they think experimentalists would work with anything. People give them anything, but no, experimentalists like myself carefully select, things that work. So today I'll be talking about these trapped ion experiments. This is like a cartoon of what goes on with the trapped ion. So the key thing is the ions are trapped above in some kind of RF Paul trap. They have the ability to do detection by fluorescence. They have control through manipulating an internal state, and they have conditional interaction between the ions due to this Coulomb repulsion. And in this particular paper, we were looking at kind of materials challenges if you wanted to build better traps and have more control of these ions. So you can build an ion trap quantum computer or quantum system out of any ion which you can laser cool. Laser cooling just requires that you have a closed transition, more or less. There might be some metal stable state you have to repump. In my group, we use mostly ytterbium-171 for quantum computing experiments. And we use calcium ions for, we have experiments using calcium ions as detectors for molecular ions. Now, the thing that I think is funny is if you look at ion trap quantum computing startup companies, the ones in the US use ytterbium, the ones in Europe use calcium. I don't know, is the calcium actually that much better in Europe? It's unclear. Eric, there's no, I guess there's a startup company in Australia that also uses ytterbium?
We are all ytterbium down under.
Yeah, exactly. So it's a good question, what's wrong in Europe? Maybe they can't import good ytterbium? I don't know. Okay, so the way we build this quantum computer with ytterbium is we use these fancy surface electrode traps, which we get from Sandia. We then are going to do Raman transitions, which I'll talk about in the next slide, where we're going to have a global beam that addresses all ions and individual beams that talk to each ion. The work I'm basically going to only talk about today is with Jung-San Kim in our joint experimental lab we have together. We collaborate a lot with Chris Monroe, who recently, during the pandemic, moved from Maryland down to Duke. So here's a picture. This is kind of the oldest quantum computing experiment in this joint lab with Jung-San. It has a standard room temperature, ultra-high vacuum chamber. Inside, there's like this PCB board, which routes voltages to this trap, which we get from Sandia. On the outside, this is like a generation of Go optics. But all the pictures I could find of the current generation optics are just CAD. So I just want you to know these like actual optics. We use these micromirrors to do the individual addressing. And then part of the reason why we work on ytterbium is that we can use for the control laser a pulse 355 nanometer laser, which is from Coherent. This laser is used to cut the masks that make computer chips in your computers. So they're actually relatively cheap for a laser, have a lot of power. You buy them off the shelf. They have like basically one key, and that's it. Okay, so for the control, again, we do these Raman transitions. It's kind of Yeah, it really is a lucky break, but it turns out that the triple YAG laser is at the perfect off-resonance frequency between these two P states to basically get rid of the second-order Stark shift. And so you become less sensitive to that. And then the way we do two qubit gates, which I'll talk about at the end of the talk in more detail, is basically the ions are pushed. They're both pushed depending on their states. And that, because of their shared motion, moves them around. And then in these pictures, which again, I'll come back to at the end, we just want at the end for them not to have moved anywhere. So they come back to sitting still. This is like community values. So like the best single qubit gates are like 10 to the minus 6. With microwaves, Raman gates now are 10 to the minus 3 for 2 qubit gates. And there's a really nice review article, The State of the Art, from 2019 from the group at Lincoln Labs, which I recommend reading for more details. So here are kind of our native gate sets that's pretty common to everyone. There's an accessible test bed at Sandia National Lab in the US called QScout. We have one at Duke called Stack, which is, I don't know, in beta. If you want an invitation, let me know. We can try some things. We have these different companies: Alpine Quantum Technologies, Oxyonics, Honeywell, which is Quantinuum now, IonQ. And there's a lot of different language support. And I just want to point out, if anybody uses Arctic to control their experiments, we have a platform called Duke Arctic Extensions, which makes Arctic much better. Yeah, in the interest of time, I'm not going to say anything else about it. So our basic rotations are, we have the Z rotation, these X and Y rotations, and then this Mølmer-Sørensen gate, which ends up being an XX spin type rotation, and we always measure in Z. That's our basic set of gates. The Z rotation just has to do with the phase of our microwave. So it's effectively perfect. Like it's like we Z rotations are more or less error-free. Rotations in the XY plane, we have an error of a few times 10 to the minus 4. Our best XX gate is about 5 times 10 to the minus 3 in Jungsong's and my joint lab. And then our best measurement, which is not the measurement we use every day, also uses these superconducting nanowire detectors to get to that. Normally, we're closer to just below 1%, like 0.5%. Okay, so now when we think about these control errors, if I just think about doing a single qubit gate, I have an error in my my Rabi frequency, which can come from the laser not being quite right, power fluctuations in the laser, all these things. I have errors in my frequencies, and then I can have errors in this relative phase. And for us, the thing we have the hardest time classically feeding back on is actually the error in the laser intensity. Because we can do it before we send the laser into the trap. There's a lot of space there. And any beam stability, upstream, downstream, can cause problems. So what's nice is that there's a way to get rid of this kind of over-rotation error based on composite pulses. So there's a really, like, if you don't know about this sequence, you should look it up, BP1, which Wimpress invented in 1994. 2004, Aram and I, working with Ike, came up with like arbitrary accurate ones. The only ones that I ever use are SK1 and BB1. BB1 is where you want everything to work regardless of how much intensity is there. SK1 is where you want the thing you're aiming at to work, but its neighbors to be suppressed. So it's like kind of a passband pulse. And then Guanghao Lo, Ted Yoder, later in 2014 showed that you could make these higher order pulses efficiently. But in practice, I've never used them. Like I mean, I've used them to test them, but in practice, these second order ones are good. What's the idea? So in this picture, you see that these different rotations of 2 pi lead to kind of these loops that push you closer to landing on this equator. But when you look just at the equator, you can kind of linearize the Lie algebra. And the original error is like you've gone too far. The second error ends up like the area of this triangle. And BB1 is you have triangles of opposite area, and so they cancel. That's it. Okay. So Robin Blumkehut, I talk with all the time, who's he's really into characterization. He has this picture of gate set tomography, which of course there was other work towards gate set tomography before. But his idea is that you just have these buttons. So your quantum computer is a set of buttons. He's like way on the gate side. So you push these buttons, and then you push them many, many times, and then from them you figure out what the buttons do. And so what we did is we said, okay, let's do that with just our regular gates. And so without any composite pulses, our regular gates are like quite high fidelity according to gate set tomography. When we apply these composite pulses, you see that the fidelity both goes up and the variance goes way down, right? So we do get better gates. If you take the output of what gate set tomography thinks these gates are, and you ask if SK1 works, the answer is no. The predicted value is it's not going to help you out, right? And so I think that's a weird thing because we have a model, we have a biased model of what we think the noise is. We can use that information to make better pulses, even when our characterization tells us not to do it, right? Characterization would say, skip it. Now, it's not exactly fair. And the reason why it's not fair is that gate set tomography assumes that every time you push the button, the answer is the same. But in reality, there's like a slowly varying, just really slowly varying intensity noise. You can think of it in our case of like the lasers just like slowly drifting back and forth. And so gate set tomography can never fix that, right? But here, but these three experiments together give us confidence that this slowly varying intensity noise is a problem. So then what can we do with our 2-qubit gates? And so what I liked, Ram's talk about the pulse inverses. So we have this thing which we usually call hidden inverses. And the idea is, for whatever reason, quantum information people love unitaries, which are their own inverse. But like no experiment works like that. Nobody nobody really has a CNOT button, right? Everybody has to construct it out of stuff. So there is a difference between CNOT and CNOT dagger, which is equivalent to the pulse inverse of the CNOT sequence. So here we apply, we have the CNOT and CNOT dagger. And so our idea was, imagine you want to make a giant controlled x to the minus I theta z, 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 z. So you have like a z rotation, here represented by z to 1 over the 16. You have this cascade of controlled knots. And if you were taking your basic quantum mechanics class, you're like, oh, I have u transforming some other unitary w with u dagger. But somehow when we write it as control knots, we're just like, oh, it's control knot on this side, control knot on that side. So now, if we add this idea of an error, which is that there's an intensity fluctuation on the laser, what we see is that the hidden inverses in standard work better on opposite sides of this angle. So if the angle is small, like it often is in quantum simulation experiments, switching to hidden inverses leads to a much higher fidelity of this whole gate sequence. And this is, simulation. So our gates are good, so we can't, if we just do this, if we just do one instance, we don't see anything. So what we have to do is we have to like multiply it up, and we multiply it up by repeating the same block multiple times, also as we've seen from extrapolation, these sort of things. And when we do this, when we first tried this in early 2020, we found that not only did it work, but it actually fixed an error we weren't thinking about. And so what this error is, this phase offset, is for my single qubit gates. Okay, so Z is really well defined because it's the clock which runs my experiment. X and Y for the single qubit gate and X and Y for the 2-qubit gate may not be the same. Because there's just like a stark shift, there's all kinds of funny reasons. So this 0.015 pi phase we saw is basically that our 2-qubit gate X and our single qubit gate X weren't the same. And so then once we see that, we can fix it, but also without fixing it, we find that the hidden inverses also fixes that problem kind of naturally. So then we looked at this again. We basically okay. I don't know. I guess I will say that the kind of frustrating thing for me sometimes with quantum control is we find this quantum control technique which fixes this problem we have with phase offset. But now we can measure phase offset. So we can just get rid of it by tuning the experiment. But we really couldn't see it before. None of our other calibration techniques saw it. So here, when we get the phase to nothing and just look at overrotation, we see the hidden inverse protocol for 2 qubits is much better than not. And our estimated fidelity improvement over, again, repeated 5 things is quite good. We do the same where we turn the overrotation error down and the phase error up. Again, we see this error is pretty good. So then what can we compare it to? So one thing to compare it to is randomized compiling. So randomized compiling gets rid of these coherent errors. That's its job. But what's interesting is for the overrotation and the phase error, where hidden inverses helps, near this small angle, it's just better to take advantage of that. Like if you are confident that is your dominant error, it's better to do that than randomized compile. On the other hand, if I have a detuning error, that is actually not going to invert when I invert my pulse, because I don't realize I have that error. And in that case, randomized compiling is like much better than trying to do these hidden inverse type of operations, right? So in the end, which thing to do really depends on your actual physical system and what the actual physical errors are. Okay, so so my student Swarnadeep, who is on that paper doing some of the theory calculation, super excited to work on like variational algorithms to test it out. And he's done this not under my supervision, but he has, in the US, we have these NSF triplet grants where you have like an extra advisor to your advisor. So his extra advisor is Raphael Puzer at Oak Ridge National Labs. So this is their work. On the left, they use the QScout testbed. And this is the QScout testbed if they don't do anything. They just use the gates that are there. And this alpha is plotting out the landscape like a slice of the variational landscape. And what you see is that the hidden inverses, the blue, is better than the random compiling, the standard. If they crank up the noise in the way you'd expect, which is just making that angle worse, of course, the separation gets larger. And then the kind of more interesting thing is they look at what happens if you just don't do as much cooling, so that your whole system is not quite as good. And in that limit, they also see this advantage, which is good. Now, on the other hand, on the this IBM experiment, on these different IBM machines, here they're just looking at how many executions you need to do to like reach the, right? So I'm doing my variational algorithm to try to reach whatever my minimum is. And what's interesting is sometimes, like on this machine, random compiling and hidden inverses are exactly the same. On these other machines, there's some difference, but they tend to the same error. And then on this last machine, hidden inverses is terrible. And it must be because the detuning is not, I mean, again, I've done no work on these papers. My impression is that it's got to be due to detuning. So it's kind of, it's interesting to me. Okay, so now, in terms of ions in motion, I just want to say a little bit more about how this works. So the idea is this carrier, this is, I stole this graphic from Innsbruck. This is like the carrier transition where you only change the qubit. This is the blue transition where when you excite the qubit, you also add a phonon. So you can think of it as like anti-Jaynes Cummings. And here, when you excite the phonon, excite the qubit, you remove a phonon. So you can think of it as Jaynes Cummings normal kind of interaction. And so the key thing that makes the coupling work is the harmonic oscillators are quantum. So in this case, we see when we cool to the ground state, the red sideband disappears because we can't go any cooler. So Mølmer and Sørensen had this nice idea that by having two-tone colors of red and blue lasers slightly detuned from the sidebands, there's an interference effect so that this gate doesn't depend on how many quanta of motion there are. And the trick is we have many more normal modes, so we have to worry about them. So how we handle this is the same as always, is we have, this is our actual Hamiltonian we're driving, so there's the spin part, and this is obviously some the oscillator parts for the different modes. It turns out because, well, basically because momentum and position commute to give you a number, it makes the Magnus expansion really good. So at second order, it just ends, and you're done. So when you do that to second order, you get a first term, which is like a spin-dependent displacement, and a second term, which is the easing type interaction between the two spins we want. And so the goal is we just turn this to 0 by integrating this out. It's the bad part, and we make this to be the angle we want. So people, like the earliest work using multiple modes here would use amplitude modulation. Mike Biersick's group worked on phase modulation. My group has been working on frequency modulation, and this is kind of like, again, our experiment with the best kind of best results. We have this discrete frequency modulation. These are pictures of the phase space trajectories. These units are quanta of position and momentum. So it's kind of funny. It looks like, you know, this mode is going all over the place, but it's still basically like the ground state wave packet moving on top of itself. It's not like it's more or less invisible. So then where are our errors coming from? So we can write down our error budget of, you know, we don't really worry about spontaneous emission yet. We have a little bit of imperfection in these solutions. Laser dephasing we were able to fix. And then our problem lately is motional dephasing. So the frequency of the trap is shifting a little bit relative to, shifting at some time scale, shifting at the time scale of our characterization. So what we've done recently is my student Mingyu. So okay, first my student Mingyu did a lot of like machine learning, batch optimization stuff. It helped a lot in theory, but in practice it didn't help. So the next thing he did is he said, well, people are working on these filter functions, so I'm going to do these sequences to get kind of contrast of different kind of higher order dynamic decoupling Ramsey type sequences, transform that into a spectral density of noise, which so you know, you get this kind of 1 over f squared sort of thing. And then to optimize the solutions so that it minimizes this noise. And when we did this work, the nice thing that happens is that when we do our budget of errors at the end, we see the experimental error goes down, which is good, and that is only due to the motional dephasing going down. So by basically figuring out the time scale at which this motion is phasing and then shifting our frequencies to like try to filter it out, we're able to get this gain. And if you're paying really strict attention, you'll notice that this number is not as good as my last number, basically the same as my last number. And so the frustrating thing is that in this particular experiment, the micromirrors cannot take that much UV power. And as a result, that fundamentally limits how fast we can drive our gates. And so at the speed we normally run of 130 microseconds per 2 qubit gate, you see that the robust and the FF robust, the dashed line and the solid line basically are the same. So there's no, at that speed, there is no gain. At the slower speed where we show this improvement, we get good agreement with the theory, but we, you know, but it's like not, it's out here. And then by switching to a different way of delivering the power, either by using a large AOM or an AOD, we should be able to increase the Rabi rate of the single qubit Rabi rate and then actually get a separation even out at very fast pulses. And so that's kind of the experimental direction we're heading. I just want to say, because it came out, I don't know, 2 days ago, when we started this whole process, our motional states had the most error. And in the process of trying to get that down and make the motional dephasing lower and lower, we got to the point where we now have very good control over our bosonic states. So we can now make entangled states between these different phonons. We have a new type of readout method where you basically, because normally we're trying to make a quantum computer, we can individually read out and control every ion. And as a result, we can actually use each ion to independently detect every mode, which we do in parallel. So this is an example of just 2-mode detection. In the paper, we also show 3-mode detection, but there's no real limit there. All right, so clean up. So whenever I talk to superconductor or semiconductor quantum people, they're always like, oh, what's your T1 or T2? And I'm like, that's just not our problem. Our problem is really the gates. Like, if I didn't have to do gates, I'd be fine. I'd make an atomic clock. I'd have a precision of 10 to the minus 18. See you tomorrow. Yeah. These slowly drifting systematic errors we can remove by pulse design, but we find an interesting balance between, like, how do we do the right characterization to get the control out? And we're looking forward to using some of these more advanced ideas for measuring filter functions and frames and this sort of thing. High frequency systematic errors, we have to eventually fix through hardware or quantum error correction. They're kind of good error models for quantum error correction. And then I think what's interesting to me is there a lot of, I have many examples in science where people did something, 10 years later, people came back to it and found something great. 10 years later, people came back to it and found something great. And there's sort of these like lulls, ups and downs. So please consider coming, since it's almost 2024, it's about time to come back to these composite pulses and try it again. And with that, I will just put this last slide. We now have a Big Duke Quantum Center. There you can see the chair of our session. We have postdocs in all possible things. So if you need a postdoc in anything, let us know. And then I'm grateful for funding from the NSF, the Army, IARPA, and the Department of Energy. Thanks.